polynomial number of states, but it's a fast polynomial. Sure. Yeah.
So in this last hybrid story,
Yeah.
doing things numerically, are you actually doing a numerical Fourier transformation, computing numerically the monodromy mean and the logarithm of the monodromy?
We don't have to do that anymore.
So instead of doing explicitly that, you're able to calculate the
Yep.
appropriate solution to the Lyapunov equation associated with the logarithm?
Yes. So here's the idea how. So we construct a moving coordinate frame around the trajectory we computed nominally, numerically, but we analytically verify at every. So first, just think about computing finite time invariance of this set. So on the edges, we have to verify the Lyapunov function is going down. We have an analytic description now as a spline representation of this cone we're trying to verify. We have the dynamics analytically. It becomes a point-wise verification that every point is going downhill on the standard Lyapunov trick. Okay? And if we've done that everywhere on the cycle, we've proven stability, local stability of the limit cycle without ever integrating it. And then if we want to prove stability contraction to the manifold, we can do it. We can't do it to tolerance if the numerical answer was wrong, but we can do it up to some small epsilon ball, for instance, verifying analytically that the Lyapunov function is decreasing up to some numerical margin around this.
So you said you can efficiently do interior estimates or underestimates. So presumably you're growing the gray region as big as you can. So what's the process by which you grow? You must have done some initial guesses, but you're improving on the guesses.
So global Lyapunov analysis is a convex optimization. There's no guesses required. For local Lyapunov analysis, you have to do some sort of iteration typically between depending on how you parameterize it. There is a convex parameterization, but the typical one, you're searching over Lyapunov functions, it's a bilinear problem. So we do typically use a Robotic or Lyapunov method to use the linearization to produce an initial guess, and then we blow it out using a bilinear search in the convex optimization. And these bilinear searches we found to be very efficient. I mean, there's no guarantee that gets to the global, but it's convex optimization, and it seems to be pretty formulated.
And in all of this, you're using some sampled or spline-fitted version of the nominal cycle?
In the limit cycle case, we do a spline, yes, and so the Lyapunov candidate might not be the optimal one, but the verification of it is exempt, right? It might not be the biggest region because we have numerical errors, but once we have an analytic description of a cone we want to verify, a tube we want to verify, that verification is exempt. Sure, yeah. We do these time invariant regions.